Let's take a look at section 4.5. And this section is rational functions. Now, a rational function means you have a single fraction. Of course, it's a function, so all the parts that go with the function hold true. Now, first thing they're asking us to do in this section is to find a domain. So, domain of a rational function. Step 1. You set the denominator equal to 0. Step 2, you solve. And then step 3, you put a slash through the equals. I take a look at page 362, number 3. Got f of x is equal to x plus 1 over x squared minus 6x plus 5. The instructions say to find the domain. Step 1, set denominator equal to 0. So we got x squared minus 6x plus 5 equal to 0. Now sometimes this may be a linear equation. This is a quadratic, so we'll factor it. This factor is using the PSD. And it factors as x minus 1 times x minus 5. Now, zero factor property says you get 0 on one side, you factor the other side, you said each factor equals 0. So I'll set x minus 1 equal to 0, and I'll set x minus 5 equal to 0. Which gives us x equals 1, and x is equal to 5. And I guess that was step 2, solve it. Now step 3 said to put a slash through the equals. So x cannot equal to 1, and x cannot equal to 5. It can equal any other value. Now I'm going to show you how to write that in interval notation, just in case the problems are looking for that. When you got two numbers like this, you go from negative infinity to your smallest number, parentheses on everything, union, your smallest number to your largest number, parentheses on everything, union, your largest number to positive infinity. And that would be interval notation. Let's look at number 4. Got f of x is equal to x plus 4 squared over 4x minus 3. And same instructions, we want to find the domain. Step 1, set the denominator equal to 0. So we've got 4x minus 3 equal to 0. Step 2, we want to solve it. This is a linear equation, so I'll take negative 3 over to the right side, becomes a positive 3. Remember, when you move anything across your equals, your sign changes. Then divide both sides by the number in front of your x. So we'll divide both sides by 4. Then you got x is equal to 3/4. Now, third step is put a slash through the equals. This is the value you cannot equal, so x cannot equal to 3/4. Now for our interval notation, when you have one number like that, you go from negative infinity up to that number, parentheses on everything, union, and then that number up to positive infinity, parentheses on everything. And those would be our answers. Let me grab a drink here. Let's take a look at finding asymptotes now. Now an asymptote is an invisible line that your graph will skim at some point. We're going to look at finding the vertical asymptote. Verticals up and down. Now, first step in finding a vertical asymptote is you factor the top, the numerator, and factor the bottom, the denominator. Step 2, cancel if possible. And step 3, set the denominator equal to 0, the bottom equal to 0, and solve. Okay, number 14. We've got page 362. Number 14 says, got f of x is equal to 4x over x squared plus 10x. Step 1, factor the top, factor the bottom. Well, the top really doesn't factor any, but the bottom I see it has a GCF. I can bring an x out. So we got 4x over x times x plus 10. That's step 1, factor the top, factor the bottom. Step 2 is to cancel. Now notice how they both have an x here? That x cancels that x. Now the reason why you can do that is because everything's multiplication. You got 4 times x, and you got x times x plus 10. So that gives us 4 over x plus 10. Step 3, set your denominator equal to 0. So we'll set x plus 10 equal to 0 and solve it, and we get x is equal to negative 10. And that's our vertical asymptote. Let's look at some of these already factored. But let's look at number 20. Maybe I'm lying to you. Let's look at number 18 first. It's a little bit more interesting. We got x squared minus 4 over x times x plus 5 times x minus 2. Step 1, factor the top, factor the bottom. Bottom is already factored, but the top I can use the difference 2 squares. It factors as x plus 2 times x minus 2 over x times x plus 5 times x minus 2. Now step 2 is to cancel. If you got something on top and the bottom they're the same, like x minus 2 and x minus 2, those are going to cancel. And you're left with x plus 2 on top, and on bottom you got x times x plus 5. Now step 3, set your denominator equal to 0 and solve. So we got x times x plus 5 equal to 0. Set each one of those equal to 0. So we got x equals 0, and we got x plus 5 equal to 0. So we got x equals 0, and x is equal to negative 5. And those would be our vertical asymptotes. Now these two happen to have something cancel, and I picked those on purpose. But you don't have to have anything cancel. If nothing cancels, you still go through the same process. You set your denominator equal to 0 and you solve it. Now what this means, we don't have to graph it, but if I were to graph it, I know there's a vertical asymptote at x equals 0. So that means my graph's going to skim it at some point right there. And there's one at negative 5. So I don't know much about this, but I know over here my graph's going to skim it at some point. We'll talk more about that later on. But that's vertical asymptotes. Now let's talk about horizontal asymptotes. I've been referring to the top of the fraction. The numerator is top, and bottom of the fraction, the denominator is bottom. So keep that in mind. Now degree, remember, is your largest power of x. There's a little bit more to that definition than that, but that's one that helps us the most in algebra. Now for a horizontal asymptote, we got 3 cases. Case 1, the degree of the top is larger. That means there is no horizontal asymptote. Case 2, the degree of the bottom is larger, or horizontal asymptote is y is equal to 0. And case 3, the degrees are the same. Now I'd like to show this with an example. Example makes it a fairly simple idea, but if I try to put it into words, talking about standard form, leading term, leading coefficient, and so forth, it gets complex. I'll make this bigger after I type it out. We got f of x is equal to 3x to the fifth minus 7x over 4 minus 2x to the fifth. So then a horizontal asymptote will be y is equal to 3 over negative 2. Okay, now degrees are the same. Degrees are the largest power of x. The degree of the top is 5, the degree of the bottom is 5. They're the same. What you do is you take, you're going to create a fraction. The horizontal asymptote is y equals, and you take the numbers off the front of the x to the largest power. So I take the 3, because it's what's before the x to the fifth, and I'll take the negative 2, because that's what's in front of the x to the fifth. And a horizontal asymptote will be y is equal to negative 3/2. Let's take a look at number 22, same page. We got g of x is equal to x plus 6 over x to the third plus 2x squared. Now if I look at my degrees, degree of the top, degree is the largest power of x, degree of the top is 1. Degree of the bottom is 3. So in this case, the degree of the bottom is larger. I don't know what it did right there. Let's try it again. Okay. Degree of the bottom is larger. That's case 2. That tells us a horizontal asymptote is y is equal to 0. And that's our answer. Now 24. We got f of x is equal to x to the fifth over x to the fifth plus x. And we're wondering about the horizontal asymptote again. The degree of the top is 5. The degree of the bottom is 5. So the degrees are the same. Remember, when degrees are the same, we create a new fraction. So we've got y is equal to this fraction. And I take the numbers off the front of the x largest power. So this will be 1, and this will be 1. And 1 over 1 is 1. So our answer is y is equal to 1. Let's look at 26. Got h of x is equal to 8x to the fourth plus x minus 2 over 2x to the fourth minus 10. So for a horizontal asymptote, we look at our degrees. Degree is your largest power of x. The degree of the top is 4. The degree of the bottom is 4. So the degrees are the same. So for a horizontal asymptote, we're going to create a fraction, and we take the numbers off the front of the x to the largest power. So I got 8 over 2, or y is equal to 4. Number 25. I know you probably don't see any 4 examples of this, but this is the other type. We got g of x is equal to x to the third minus 2x squared plus x minus 1 over x squared minus 16. And still asking for the horizontal asymptote. The degree of the top is 3. The degree of the bottom is 2. So the degree of the top is larger. Degree of the top is larger. Horizontal asymptote is none. So the answer here, there is none. Let me clear off those, and we'll look at slant asymptote. This book refers to it as oblique. Okay, slant asymptote. And again, it's referred to as oblique asymptote in this book. Note, in order to have a slant asymptote, the degree of the top must be exactly one larger than the bottom. And how you find a slant asymptote is you use long division and drop the remainder. So use long division, drop the remainder. Okay. Let's take a look at an example of this. Let's take a look at number 28. We got f of x is equal to x squared minus 6x over x minus 5. And the instructions say determine the oblique asymptote. The degree of the top is 2, degree of the bottom is 1, so it is exactly one larger. So it does have a slant asymptote. So I'll use long division. Now notice what's missing here. We got an x squared, we got an x, but we don't have the no x, the constant term. So I'm going to put a 0 placeholder. Now remember the long division, we take a look at the first term of each, decide what to put up on top. We ask ourselves what times x gives us x squared, and that's x. Now whatever you put up on top, you're going to multiply by what's out in front. X times x is x squared. X times negative 5 is negative 5x. Now we're going to subtract that line. And when you subtract, that flips sign, so this positive x squared becomes a negative x squared, and the negative 5x becomes a positive 5x. Now x squared minus x squared drops away. Negative 6x plus 5x gives us negative 1x, or negative x, and then I'll bring down the 0 placeholder. Now again, we look at the first term of each, decide what to put up on top. You ask yourself what times x gives you negative x, and that's negative 1. Whatever you put up on top, you're going to multiply by what's out in front. Negative 1 times x is negative 1x, or negative x. Negative 1 times negative 5 gives us a positive 5. And I don't know why I put an x there. It's just a 0. Okay. Then I'm going to subtract that line, which means flip signs. So this becomes positive, this becomes negative. Negative x plus x drops away. 0 minus 5 is negative 5. Now our instructions say to drop the remainder. So we drop that, and our slant asymptote is y is equal to x minus 1. Now I'm going to graph one of these by hand, just because I want to demonstrate what in the world are all the different components used for. So let's look at number 66. We've got f of x is equal to x minus 1 over x squared plus 2x minus 15. Okay. First off, I'm going to find the vertical asymptote. Remember, our first step is to factor the top, factor the bottom. Top can't factor, but the bottom is a PSD. So that factors as x plus 5 times x minus 3. Obviously, nothing will cancel. So we go to step 3 of the vertical asymptote. We set our denominator equal to 0, and we solve it. Now, since it's already factored, it's in perfect form. I'm going to set each factor equal to 0. So I got x plus 5 is equal to 0, and x minus 3 is equal to 0. Which means I got x is equal to negative 5, and x is equal to positive 3. And those are our vertical asymptotes. Now, horizontal asymptote. Degree of the top is 1, degree of the bottom is 2, so degree of the bottom is larger. If your degree of your bottom is larger, then your horizontal asymptote is always y is equal to 0. Now, there is no slant asymptote. The degree of the top must be exactly 1 larger than the bottom. Now, our x-intercept. When you're finding intercepts, you always plug 0 in for the other variable. So if we're finding the x-intercept, we plug 0 in for y. So I got 0 is equal to x minus 1 over x squared plus 2x minus 15. Now this is a rational equation. And to solve a rational equation, you multiply everything by the LCM of all your denominators. Now we only have one denominator, so that is our LCM. So we'll multiply that times 0. And we'll multiply it times this fraction. Now when I do that, these are going to cancel. And 0 times anything is 0, so we end up with 0 is equal to x minus 1. When you're dealing with rationals, it doesn't apply all the time, but when you're dealing with rationals, when you're finding the x-intercept and you set the fraction equal to 0, you can always just set your top part equal to 0. You don't even need to show that step. And our x-intercept is x equals 1. Now our y-intercept. Again, you always plug 0 in for the other variable. Remember, f of x is the same as y. So you plug 0 in for x. So I got y is equal to 0 minus 1 over 0 squared plus 2 times 0 minus 15. Those zeros all cancel, and I got negative 1 over negative 15, which gives us a positive 1 over 15. And that's our y-intercept. Okay. Vertical asymptote, negative 5. Don't know much about this graph, but I know it skims this line at some point. X equals 3. Again, I don't know much about it, but it skims that at some point. Horizontal asymptote was y is equal to 0, which is the x-axis, so it's going to skim that at some point. Now our x-intercept was x equals 1, so it passes through here. Our y-intercept is 1/15, which is really small, probably about right here. Okay. Now let's come up with our graph. I know it skims these lines here. I know it has passed through here and here. So if it skims this, it's coming down here, it's passing through there, passing through that, and then skimming that. So when I say skimming, it's coming real close to it, but never touching and never crossing it, just continuing forever. Now over here, the question is whether it's up here or whether it's down here. And there's really no way to, I mean, once you get comfortable with graphing a few of these, I'm pretty sure it's down here. But the only way to know for sure is to plug in an x value. Now if this is x equals negative 5, then I'm going to plug in negative 6. And we're going to plug that into our original function. So original function was x minus 1. Actually, I got it right here. That's the same there except for these are x's. So x minus 1 over x squared plus 2x minus 15. So I'll plug negative 6 in. I got negative 6 minus 1 over negative 6 squared plus 2 times negative 6 minus 15. It gives us negative 7, 36 minus 12 minus 15. Negative 6 squared is 36. 2 times negative 6 is negative 12. Negative 12, negative 15 is negative 27, plus 36 is 9, I believe. So negative 7 ninths. Let me double check that. Yeah, negative 7 ninths. So at negative 6, we got negative 7 ninths. So that's going to be down here. Which tells me then it's passing through that point, and it has to skim these. It's going to look something like this. Now I won't waste the time, but we'd plug in a point over here too. Since this is 3, I might plug in 4. And what I'm going to find is the graph will be up here. And that would be our graph. And that's what asymptotes are used for. Now to graph this by hand, you have to use all those different components. To do it on the calculator, the one thing you have to remember is put parentheses around the top, parentheses around the bottom when you plug it in. So we're going to go to y equals clear, beginning parentheses, x minus 1, closing parentheses, divided by, beginning parentheses, x squared, plus 2x, minus 15. And again, I put parentheses around top, parentheses on the bottom. And then graph. Now the calculator will sometimes give you a poor graph. Now it's probably right here. That should be a little further down toward the x-axis. I'd have to plot points to see that. But it's skimming this, and it doesn't just stop like this implies. It goes up forever. This down here is going down forever. You can see here is like a little piece of it here, but really hard to determine. And then a little piece here. This is a perfect example why asymptotes will give us a better picture. It's a little bit harder, but gives us what we want. And that's really it for that section. So let's take a look at the next section. Next section is 4.6, polynomial inequalities and rational inequalities. Okay, so polynomial inequalities. Our first step is to get everything on the left side, 0 on the right side. This process is based upon there being everything on the left side, 0 on the right side. Step 2, set the left side equal to 0 and solve. These are going to be called our critical values. Step 3, using the x-axis, the critical values, and the graph, then determine the answer. If you got less than or equal to, then your answer is below the x-axis. And I'll talk more about that once we look at a problem. If you got a greater than or equal to, your answer is above the x-axis. If you got less than or greater than, you're going to use parentheses. If you got less than or equal to or greater than or equal to, you'll use brackets. Okay, so let's take a look at a problem. And let's look at number 28. This is on page 373. We got x squared minus x minus 6 is greater than 0. Step 1, get everything on the left side, 0 on the right side. That's done. Step 2, set the left side equal to 0 and solve. So we got x squared minus x minus 6 equal to 0. Now this will factor. If it didn't factor, you might have to use quadratic formula. But this will factor using the PSD. It factors as x minus 3 times x plus 2 equal to 0. Now the zero factor property. You get 0 on one side, you factor the other side, you set each factor equal to 0. So I'll set x minus 3 equal to 0, and I'll set x plus 2 equal to 0, which gives us x equals 3, and x is equal to negative 2. Step 3. Using the x-axis, here's the x-axis, our critical values. Now I want to range them from smallest to largest. Negative 2 comes first on our x-axis, and 3 comes second. Now what these do is they split them up into intervals. Clear over here is negative infinity. Clear over here is positive infinity. And the graph. So we have to graph it. Now where you want to graph it is where you got everything over on the left side and 0 on the right side. So I want to graph that. So I go to y equals, clear. I got x squared minus x minus 6, and then graph. Now you'll find where it crosses the x-axis will be your critical values. If I were to sketch my graph on here, it would look like this. And do not spend any kind of time trying to make this look good. That's not the point of this. But that's what our graph looks like. Now, our problem was a greater than. If I come down here, greater than says your answer is above the x-axis. So I'm looking for my graph is above the x-axis. Well, it's above in this interval, and it's above in this interval. Now this first interval is negative infinity to negative 2. The second interval here is 3 to positive infinity. Now infinities always have parentheses on them. Greater than. Greater than tells us to use parentheses. So we'll put parentheses on negative 2 and 3. And if you got 2 or more intervals, you connect them with a union. And that would be our answer. And let's take a look at number 32. That x squared is less than or equal to 1. Step 1, get everything on the left side, 0 on the right side. So I'm going to take that 1 and move it over to the left side. Remember, when you take anything across your inequality symbol, the sign changes. So the positive 1 becomes a negative 1. Step 2, set the left side equal to 0 and solve. So I'll set x squared minus 1 equal to 0. And this is actually, you could factor it and solve it that way, or I could use the square root property. Square root property, I take negative 1 to the right side and becomes a positive 1. And square root property says we drop our squared and you put a plus or minus square root on the other side. So we end up with x is equal to plus or minus 1. Well, here's our x-axis. Our critical values are negative 1 and 1. So I'll put negative 1 first and positive 1 second. Remember, these split them up into intervals. Clear over here is negative infinity. Clear over here is positive infinity. The point where we want to graph it is where we got 0 on one side. So we want to graph x squared minus 1. So go to y equals, clear, x squared minus 1, and then graph. Again, you'll find it crosses at the critical values. So our graph more or less look like that. Now this problem's a less than or equal to. Less than or equal to says your answer is below the x-axis. If I look where my graph is below, it's in this middle interval. If it's below in part of it, it's below in all of it. If it's above in part of it, it's above in all of it. There's no mixture within one interval. So this answer is from negative 1 to 1. Now it's a less than or equal to. Less than or equal to tells us to use brackets. So we'll put brackets around negative 1 and 1. And that would be your answer. Now all these are the same way. You have to do different factoring. Some of them use square root property. I don't think I see any that use the quadratic formula. Some you may have to factor by grouping, but they're all of the same type. Now let's take a look at rational inequalities. Clear that off. Okay. Rational inequalities. Step 1, get everything on the left side, 0 on the right side. Step 2, get a single fraction on the left side. Step 3, factor the top, factor the bottom, set each factor equal to 0, and solve. And again, these are our critical values. Then our last step is still the same, but it becomes step 4. Okay, so let's take a look at some examples. Let's look at 57. We've got 2x over x minus 4 is greater than or equal to 0. Maybe I don't want this one. I'll look at it second, but it isn't a good first example. Let's look at number 53. Now 1 over x plus 4 is greater than 0. Step 1, get everything on the left side, 0 on the right side. Everything's on the left side, 0's on the right side. That's done. Step 2, get a single fraction on the left side. Well, we have a single fraction on the left side, so that's done. Step 3, factor the top, factor the bottom. They're factored as much as they can be. Set each factor equal to 0. Now, I don't need to set the 1 equal to 0 because there's no variable up there. So I'll just set the x plus 4 equal to 0, which gives us x is equal to negative 4. Now step 4, using our x-axis, our critical value, so here's negative 4, and that's going to split them up in intervals. Clear over here is negative infinity, clear over here is positive infinity. Now when you graph this, you want to graph the point where you have 0 on the right side, which is our very first step. And a trick to rationals is put parentheses around top, parentheses around the bottom. Now if you just have a single number like 1, you don't actually need to put the parentheses. It doesn't hurt anything. So to graph this, I go to y equals, clear, 1 divided by, beginning parentheses, x plus 4, closing parentheses, and then graph. Now, here's our critical value, and I see to the left of it, it's below the x-axis. So I'm going to put a little mark for below. I don't care about what the graph looks like. I'm just marking above and below. To the right of it, I see it's above in part of the interval, so it's above in all the interval. Okay, now we're looking for a greater than. Greater than in our table says our answer is above the x-axis. Here's my x-axis. It's above right here. So this interval would be my answer. So it goes from negative 4 to positive infinity. And infinities always have parentheses, and greater than tells me that I need to use parentheses. So that'd be our answer. Now if I look at a little harder one, let's look at 63. That combines that first one I was going to show with a little harder one. Okay. Step 1, get everything on the left side, 0 on the right side. So I'll take this 3 and move it over. So I'm going to have x plus 1 over x minus 2 minus 3 is greater than or equal to 0. That's step 1. Step 2, get a single fraction. Well, we're going to rewrite this as negative 3 times x minus 2 plus x plus 1 over x minus 2. This is the mixed number rule. You take the number to the side, you multiply it times your denominator, you add your numerator, and then your denominator stays as is. And then greater than or equal to 0. Negative 3 times x is negative 3x. Negative 3 times negative 2 is 6, plus x plus 1 over x minus 2. Negative 3x plus x is negative 2x. 6 plus 1 is 7 over x minus 2. And we got our single fraction. You can't work these unless you get a single fraction, because that single fraction means a rational. So you can't follow the steps for solving a rational inequality if you don't have a single fraction. Step 3. Factor the top, factor the bottom. There's not much I could do. I could factor a negative out of the top. I don't think it'd help me a whole lot. So we'll set each factor equal to 0. So I got negative 2x plus 7 equal to 0, and I got x minus 2 equal to 0. Now take negative 2x over, so we got 7 is equal to 2x. Divide both sides by 2, and we got x equals 7/2. This one take negative 2 over, and we get x is equal to positive 2. Step 4. Using our x-axis and our critical values, our smallest critical value is 2, so I'll put that first. Our next one is 7/2. Remember, these split them up in intervals. Clear over here is negative infinity, clear over here is positive infinity. I want to graph at the point where I have 0 on one side, so I'll just use this last form because that's what we're used to seeing. Trick to it again is put parentheses around top, parentheses around the bottom. Other than that, you plug it in as you see it. So go to y equals, clear, beginning parentheses, negative 2x plus 7, closing parentheses, divided by, beginning parentheses, x minus 2, closing parentheses, and then graph. Okay, we said our first critical value was 2. 2 is right here, and definitely to the left of it is below the x-axis. So a little mark for below. Between 2 and 7/2. Here's 2, and here's 7/2. I see it's above. And greater than 7/2, over here I see it's below. So if it's below in part of it, it's below in all of it. Okay, we're looking for greater than or equal to. If we look at our instructions, that tells us our answer is above the x-axis, which is this interval right here. So we're going to go from 2 to 7/2. Now, greater than or equal to tells us to use brackets. So I'll put bracket on the 7/2, and I'll put parentheses on 2. And that's our answer. Now, you may be wondering, why did you put a parentheses on 2? I thought you just said that they're supposed to be brackets. There's a note with this. It says, any critical value that comes from the denominator always has a parentheses on it. The x minus 2, when we set that equal to 0 and solved it, that's where we got the x equals 2. It came from the denominator. If you plugged it back in your original problem, you would have 2 minus 2, which is 0, and you can't have division by 0. That's why it always has to have a parentheses on it. Let me clear this off. And we're ready for the next section, 5.1, I believe, inverse functions. Now, there's a lot to inverse functions. And so we'll take a look at all the different pieces. And looks like the next section is mainly graphing. Okay, inverses of points. what you do is you interchange the x's and y's into points. So let's take a look at an example of that. Number 2 on page 400. We got 0, 1, 5, 6, and -2, -4. And it says find the inverse of the relation. Well, I said you're going to interchange x's and y's, swap them. So 0, 1 becomes 1, 0. 5, 6 becomes 6, 5. And -2, -4 becomes -4, -2. And that'd be my answer. Now, we're going to see a similar type thing when we're talking about equations. So inverses of equations. Specifically, we're talking about relations here, not talking about functions yet. You're going to interchange, swap the variables, the x and y's. For example, page 400, number 7, we got x third y is equal to -5. So the inverse of this relation, we swap the x's and y's. So the x becomes y. So we got y to the third, and this y becomes an x, is equal to -5. And that's our answer. Let me grab a drink here. Some of these problems involve us graphically determining the inverse. So graphically, if I had a problem, for example, that looked like this. And I'm not drawing this very well. You have to use your imagination here. This is a line y is equal to x. Inverses are symmetric to this line. What that means is that I can take this part of the graph here and I can flip it across that line. Now the point swap, so that helps. That's 1, 2, so I'm looking for 2, 1. You see, if I take this blue line and I flip it, reflect it across the line y is equal to x, it'll give me this. And even if I take this little piece down here and I flip it, reflect it, it'll give me that. So the green is going to be our inverse. So that's what it means to graphically be inverses. Now, some of these are asking us to determine if it's one-to-one. So let's talk a little bit about that. And now when we talk about a one-to-one function, definition of that says for every x there is only one y, and for every x there's only one y, and for every y there is only one x. It's a very hard definition to use. An easier definition of one-to-one function says if you have any of the following, it is not a one-to-one function. So if you have x to an even power, if you have y to an even power, if you have the absolute value of x, you have the absolute value of y, if you have the plus or minus symbol. Okay, those are the items you cannot have unless there is a condition put on x. What I mean by that is if you had, for example, y is equal to x squared plus 1, the fact that it has an x to an even power means it's not one-to-one unless I put a condition like saying where x is greater than 0. Okay, let's use this definition for our problem then. This is on page 401, number 22. We got g of x is equal to 3x squared plus 1. Has x to an even power. So response that asking if it's one-to-one, this is not one-to-one. Now we have a graphical way to determine something's one-to-one. We had a vertical line test, told us if something was a function. We got the horizontal line test. This says if any horizontal line intersects the graph at 2 or more places, then it is not one-to-one. If I looked at, for example, number 26. Our graph looks like this. Let me draw that a little bit better. If I start drawing horizontal lines, draw one here, it intersects one place, draw one here one place, draw one here one place, no matter where I draw a horizontal line, the most it'll intersect is one place. Then in response to your question, determine whether the function is one-to-one. This one is one-to-one for that reason. Now on the other hand, number 28 looks something like this. And if I draw a horizontal line right here, it intersects at 3 places. And what this says is if any horizontal line intersects a graph at 2 or more places, then it is not one-to-one. So this is not one-to-one. So you just look at the graph and you see if you can draw a horizontal line somewhere. There's some of them that want you to graph these and then determine whether it's one-to-one, so you just plug it in your calculator and see. I'm looking for the problems where it asks you to find the inverse. That looks like the next page. So let me clear this off. Now the reason why we care about one-to-one, before you could leave that, if it is one-to-one, then it has an inverse. If it is not one-to-one, then no inverse. Some of the problems may ask you to find the inverse if it's 1 to 1. If you look at page 402, number 65, for example, I notice right away it has x to an even power, so it's not 1 to 1 and there's no inverse. I shouldn't even try to find it. Now, finding an inverse. Step 1 is you, of course, it must be 1 to 1. That's with the note up there. But step 1, you replace f of x with y. Step 2, you interchange x and y. Step 3, you solve for y. And step 4, you replace y with your inverse notation. Now your inverse notation looks like f to the negative 1 power. It's not negative 1 power. It's purely notation. We're not going to look at any problems dealing with this, but there is a step 5 that says, if necessary, use the graph to figure out how to make the inverse 1 to 1. And I got some videos in that the full-blown YouTube video that I put links out to that go into all these different cases. So, okay, let's look at number 58. Got f of x is equal to 5x plus 8. And we want to find the inverse. It's 1 to 1 because it doesn't have any of those bad items we mentioned. Step 1. Replace f of x with y. So we've got y is equal to 5x plus 8. Step 2, interchange x and y. So we'll have x is equal to 5y plus 8. Step 3, solve for y. So I'm going to take the 8 over. So I got x minus 8 is equal to 5y. And then I'll divide everything by 5. Keeping in mind there's a 1 in front of your x. So this gives us 1/5 x minus 8/5 is equal to y. And then step 4, put your inverse notation in. So we replace the y with our inverse. So the inverse of f is equal to 1/5 x minus 8/5. And that would be our answer. Let's take a look at 64. We've got f of x is equal to x plus 5 to the third power. Want to find the inverse. Of course, it's okay because it has an odd power. It doesn't have an even power. Remember we said you can't have an even power. So step 1, replace f of x with y. So we've got y is equal to x plus 5 to the third. Step 2, interchange x and y, swap them. So we got x is equal to y plus 5 to the third. Step 3, solve for y. This is going to become y plus 5 to the 3 over 1. Now we want to get rid of that exponent. So what we can do is we can take both sides to a power equal to the reciprocal of it. So we'll take both sides to 1/3 power. So I got x to the 1/3 is equal to y plus 5 to the 3 over 1 raised to the 1/3 power. And when I do that, those 3's cancel and those 1's cancel. And we got y plus 5 is equal to, and x to the 1/3, I can rewrite that in radical form. That's cube root of 1. Remember, whatever your denominator is, that goes in your index. Or that goes in a slot, that's your index. Whatever power is on top goes right here, which is simply the cube root of x. But I'm going to take the 5 over, so we got negative 5 plus the cube root of x is equal to y. And then step 4, replace y with your inverse notation. So we got the inverse of f is equal to negative 5 plus the cube root of x. And that's our answer. Let's go over to 5.2 now. A lot of 5.2, I'm not going to show it by hand. A lot of 5.2, you just plug in your calculator. You clear this off. And let's take a look at page 412, number 2. We got e to the 10th power. And it says to find each of the following to 4 decimal places using the calculator. Now how you get e on your calculator is it's second ln. So I'm going to exit out of graph mode, so I'll do second mode. And I'll do second ln, and that accesses the e above it. You see on mine it says e caret beginning parentheses, and we'll put the 10th power. And then press enter. So this is equal to 22,026. And how many decimal places? 4 decimal places. 465. And then I'll round up, so that's 8. And that would be our answer. Now some of these other ones are want you to graph them, like number 12. We've got f of x is equal to 5 to the x power. So I'm going to my y equals, clear. Now I got 5 to the x power. Now this is an exponential function. What makes it an exponential function is you got a variable in your exponent. So I do 5 caret x, and then graph. Now these graphs never just stop. So that right there keeps going on forever. It just got so close to the x-axis it looks like it's one with it. Let's look at number 24. We've got y is equal to 2e to the negative x. So if I go to y equals, clear. Now the e, when I do 2, to get e I have to do second ln, same as before. And that puts my e caret beginning parentheses, and then I'll put a negative x, and then press graph. You're going to find most of these graphs look pretty much the same. This is flipped across the y-axis, looks like. And one more. Number 34. This one's got something unique about it. We got f of x is equal to 2 to the x minus 1 power minus 3. Now the trick here is anytime you have more than a single number or a single variable in your exponent, you want to put parentheses around it. So when I plug this in, I want to put parentheses around the x minus 1. Other than that, you enter it as you see it. So press y equals, press clear. 2 caret, and then beginning parentheses, x minus 1, closing parentheses, then minus 3. And then graph. And that would be our answer. And that's how you you graph those particular ones. And that's really all that section is graphing. So, well, that's the last section for this week. I looked and there was 4 sections, so that kind of gives you a start. And then from there you can read the book, you can watch the videos that kind of help you over maybe the other rough places.